Thank you for joining Calibration 101 webinar on Why Calibrate. A presentation today will be run by Tyler Pruitt, who will help answer questions at the end, and myself, Joshua Quain, who will present all the slides. We will do our best to keep this presentation under the time we projected. If for some reason you missed part of the presentation, we will be sending a link at the end to an on-demand recording of this event, along with the slide deck. So during the presentation, please use the chat box on the side to make comments and ask questions as they come up. You can also use the hashtag #VideoCalibration for questions and comments on Twitter. We'll go through them at the end of the Q&A session and live during the Q&A session and answer as many as we can. If you would like to see more presentations like this on different topics, please feel free to suggest what you would like us to cover. Today we're going to cover the who, what, and why of calibration, how calibration is used in various professions, calibration methodologies for various setups, and we'll talk about the future of calibration. On to the basics. So what is display calibration? Display calibration is optimization of display settings so that the output of a display better matches an established standard. In general, adjusting the following settings of a display to improve the look of its content. Here are a few of the different setting options. And here's a quick before and after example of how a display calibration improves the picture detail and the black levels on this display. On the left, you can see that there's a lot of loss of detail in the dark shadows. And on the right, you can see more of the tunnel, and you have a better sense of depth in the picture. So what are color standards? Color standards are a set of rules established by the international organizations that dictate the mathematical values of a specific color. For video output, that's Rec 709 or DCI P3. For PC output, it's sRGB or Adobe RGB. Without color standards, there would be no basis for display calibration. The goal of display calibration is to match a display's output to a specific color standard, so everyone who calibrates to these standards will in effect have matching displays. Most all video displays, broadcast monitors, and computer monitors are not calibrated precisely at the factory. Every display exhibits different color characteristics. Calibration is done in an effort to standardize digital content across all displays and monitors. Here is an example of what the image looks like on a non-calibrated white LED LCD display. The left image is overly blue, and the right image is more natural and realistic looking. So who should calibrate? Well, anyone whose work depends on the consistency of their display's color output. This includes production, post-production, and broadcast professionals, along with photographers and designers, medical imaging specialists, geospatial intelligence, anyone who wants their display's output to match that of a professional. Of course, this also includes the home theater enthusiasts who are on the consumption side, prosumer photographers, as well as audio-video professional calibrators. Calibration benefits include having the output of a calibrated video monitor in one studio match that of another studio across the globe. And of course, seeing proper detail and dim shadows in the example before, and peak white levels, correct gamma, correct color, and for professionals, having improved workflow efficiency. Here is an RGB chart showing before and after calibration results. This is just an example. The red, green, and blue bars show the balance of white color, and the delta E chart shows the amount of error in the display for these measured points against the standard. Here is an example of a laptop measured out of the box on the left. The round dots are the measured values, and the square boxes are the target values. And on the right shows the correct color temperature in the center white point, and the color gamut triangle shape is showing the position of the primary and secondary colors. For content creators, this helps give greater confidence in their work and credibility within the community. Alright, so now we're going to go ahead and dive a little bit into calibration by display type. To start off, we will cover HDTV flat panel displays and projection systems. Every display type requires a different method for calibrating the color's output. The method used depends on the following. The video source is the content from a Blu-ray player or a computer, a video output device, or something else. And the native display settings. What picture settings are available to the user? HD TV flat panels and projectors, often fed from a media player, have their own adjustable picture settings. These picture settings are adjusted so that the output closely matches that of the selected color standard. Either a standalone pattern source or a Blu-ray DVD disc can be used to generate these patterns for calibration. Now, because the display's own internal settings have been adjusted or calibrated, the calibration remains in place once the pattern source is disconnected. The pattern source generates the patterns on the screen. The meter takes readings of the luminance and chromaticity values for the display's performance for that pattern. CalMan software uses the meter readings to inform the user, with the charts and graphs, of the display's performance and the degree to which it varies from the selected standard. Either the user adjusts the display's settings based on this info, or the software can conduct the adjustments automatically if it's a display that has AutoCal support. Here's an example of a workflow that would be used in this particular scenario. This is the System Integrator Advanced workflow. Now we're going to go ahead and switch gears a little bit and talk about computers and connected computer monitors. Because computer monitors are often lacking in picture settings, calibration data is instead stored in the computer, not the monitor itself. This calibration data takes the form of a 1D LUT and ICC profile. In most cases, the calibration data is applied to the output of the monitor only when the monitor is connected to the host computer. The calibration does not stand independently as it would with an HD TV display in the previous examples. Here is one common setup. You have a Windows laptop driving a second monitor, and CalMan is running on the laptop. Or you could have CalMan running on a laptop calibrating a remote computer on the same network. Or a laptop calibrating a remote computer with a connected monitor. For all scenarios, the pattern source, which is CalMan Client 3, generates the patterns on the screen. The meter reads the luminance and chromaticity values for the display's performance for that particular pattern. CalMan software then uses the meter reading data to create correction data unique to this display's color performance in the form of that 1D LUT and the ICC profile that then gets stored in the operating system for the remote computer. Here's a screenshot of one of the workflows used for calibrating laptops and monitors connected to desktop computers. This is the Monitor Advanced workflow within CalMan. Now onto video monitors or broadcast monitors, which commonly have a video output device driving them. The native display performance can vary greatly due to differing display technologies. There are all sorts of displays in the market now. You have OLED, blue-green backlight displays, white LED LCDs. There are so many display technologies. Broadcast video monitors are fed by the video output device, and they may or may not have internal picture settings available to the user. Because these internal settings are often unavailable and the source or the video output device has no adjustment settings, a different method must be used. The method is a correction matrix, or a 3D LUT, specific to the unique color characteristics of the monitor is generated on the secondary computer. This 3D LUT is then uploaded either into the monitor itself, an external LUT box that's in the source path, or a video editing software program such as Blackmagic Design, DaVinci Resolve application, or Assimilate Scratch. Here's a basic configuration for a smaller studio. They have a Mac running a VMware Fusion with Windows and CalMan, and they have Virtual Forge generating the patterns out of the output device from the Mac operating system, or you could be using the Resolve or Scratch CalMan plugin to generate these patterns, and the meter is taking readings of the video monitor. In this system, you have CalMan running on a Windows computer calibrating the video monitor over the network by talking to the MacBook Pro. The pattern source, which again is the Virtual Forge, generates the patterns on screen from the Mac through the video output device. The meter reads the luminance and chromaticity values for the display's performance for that particular pattern. CalMan software uses this meter reading to create correction data unique to the display's performance. The correction data or matrix is called a 3D LUT. The user then uploads this correction file, or the 3D LUT, to the finishing software, which could be either Resolve, After Effects, Scratch, There are many other applications that support this technology. Or even some software where you could load the LUT automatically into the display itself. Examples would be like the Panasonic broadcast monitor, which supports 3D LUTs. Now we're going to go ahead and show you two complete editing systems, a laptop computer setup and a tower setup. One is with a laptop driving computer monitors plus video displays, and the other is with a tower or desktop computer driving computer monitors and video displays. In either system configuration, the laptop or desktop, for the first pass, you'll want to optimize the internal controls of the flat panel or the client viewing monitor, and this typically involves setting things like brightness, contrast, color temp, color space, aspect ratio, and then balancing the white point with RGB controls. Then you would build a corrective 3D LUT to further fine-tune the colors, and this can be loaded into popular tools like Resolve, Scratch, After Effects, and many more. For a complete list, you can visit our website at www.spectracal.com, or you can navigate to the support page and see all the different display technologies and software applications that we have. The best way to do it really is to add a LUT device, like an IS Mini by Fujifilm or AJA LUT box. The benefit for this is that you can have a calibrated monitor for any application that you're using, versus just the one application that has the corrected 3D LUT. Now for computer monitors, you want to optimize the internal controls first, if they have any. On a lot of displays, they may not have them. For example, in the Apple Cinema display, there's 0 controls, so everything's done in the graphics card of the output of the computer monitor. So you want to get the display as close as you can if there are controls. If there aren't, then you're just set with the 1D LUT and ICC Pro from the graphics card. You want to set the backlight level to match the output of the other display systems. Then you want to calibrate the 1D LUT on the graphics card for grayscale and gamma and create an ICC profile to be loaded into the operating system. For video monitors, most of them have some sort of basic calibration controls, typically not as many as an HDTV or projector. And these displays are usually pretty linear in color, so you always want to check some of the preset modes in the display before doing any calibration to find a preset that is closest to the color standard you are targeting. Oftentimes you can find a preset on these monitors that is really close without having to do much internal optimization at all. Most of the work for correcting the reference monitor is with a 3D LUT, and you can create one for editing software, or you can add a LUT box to the source path and create a corrective LUT here, or in some cases with newer monitors, you can load a corrected 3D LUT directly into the display itself. This is the way most display manufacturers are moving forward into the future. Here's a list of some of the display manufacturers currently making displays with built-in 3D LUT capabilities. Expect to see this list double or maybe even triple in 2015. Currently there's Panasonic, TV Logic, Flanders Scientific, EZO, and Dolby. And here are some of the manufacturers making external 3D LUT devices for inserting between the source and the display. AJA makes a great LUT box. Fujifilm makes the IS Mini. The neat thing about that is it also doubles as a pattern generator, has SDI and HDMI output. There's the Blackmagic Design HD Link Pro. Pandora makes a device called the Pluto. And for those of you that have been around for a while, there's the Davio, and it also doubles as a pattern generator. By the way, it works beautifully with Cowman. And here are the common 3D LUT file types supported by most of the creative and editing software applications. As you can see, this list is quite extensive. And if there's a particular 3D LUT file type that's not in this list that you need, you can always reach out to us and let us know what you're looking for. It's not hard for us to add new LUT formats since we've covered most of the common different types here. And another thing to mention too is that since we have a few here that are generic formats like CSV, there are a lot of third-party applications where you could output a LUT from Calman into a CSV file, bring it into another utility, and then convert it back out to whatever you need for your particular use case. Alright, the world is changing. So a million years ago, basically like 2012, you had to use the display's calibration controls because that's really all you had. It was an iterative process and it took a lot of work to be a master of. Nowadays, that isn't the case. With 3D LUT technology, it's more powerful, more accurate, and reduces a lot of human error. You don't have to be a color scientist or a professional calibrator anymore. You can set up the meter, set up your pattern source, select the particular LUT format, and push one button, and it will just run until it's complete. Take the file, load it into your application, your software, or your 3D LUT device, validate your color performance of your monitor, and then get back to work to the important things at hand. I just want to thank you for coming today. We're going to go ahead and go through some of the questions. Feel free to type in anything you have that you want to comment on, or you have a question on, or something that's been, you've been curious to find out. Type that into the chat box. We're going to go through and answer these as they've come in. After the presentation, we're going to go ahead and send you a copy of these slides and a link to the on-demand recording. Mentioned that in the beginning of the webinar. We would like to continue to have this discussion, and so please feel free to connect with us through one of our social media platforms. You can follow us on Twitter, connect us on Facebook. We've got a great page on LinkedIn where we're having discussions on display technology. We're talking about video calibration. So we'd love to just continue this discussion with you. And thanks again for joining us. Now here's Tyler.
Thanks, Josh. The first question was, what's the difference between a 1D LUT and an ICC profile? Essentially, a 1D LUT is a 1D ramp. 1D means it's from black to white. It only fixes the grayscale and gamma and white point. An ICC profile is a way to characterize the display so then software knows what the display is capable of, so then the software or the operating system itself can properly do a color transform to display the colors correctly. Our PC calibration solution uses a 1D LUT and an ICC profile to properly calibrate the displays, whether it be for a Mac or a PC. The second question was, can you walk us through calibrating a computer monitor with CalMan? We actually did that. We have a YouTube video that I calibrated a MacBook Pro over the network using a Windows laptop. So that's on our YouTube page. And it's a complete walkthrough. It's like 12 minutes long. It explains every step. The next question was, what's the difference between a 1D LUT and a 3D LUT? A 1D LUT only fixes the grayscale, gamma, and white point. A 3D LUT covers the entire color space, including that area. A 3D LUT adjusts the complete volume of the color space. And depending on how many points the 3D LUT is, determines how many adjustment points inside. They go from all the way down from a 5-point cube, which is 125 color points in the volume of the color space that we can adjust, up to 65 points, which is 280,000 adjustment points in the color space. The next question was, what is the recommended gamma for PC video editing? Unless the show you're working on or the content you're working on, somebody's requesting a specific gamma, almost everybody that I talk to in Hollywood is now using BT 1886 gamma. For legacy reasons, or if production company started on a show with a certain gamma and now, since BT 1886 has been adopted, they're still making the same show, they might use a power function gamma like 2.2 or 2.4 because that's what they were using before. But almost all new stuff, people are using BT 1886. The last question was, is it okay to use HP's Dreamcolor 2 Z27X as a grading monitor for Resolve? And this is a pretty common question because not everybody can afford a broadcast OLED to use as a grading display. The Dreamcolor 2 is a great display. The one thing it doesn't have is SDI, so you'll have to use some type of way to convert from SDI or use an output device that has HDMI that will feed into the Dreamcolor's HDMI. But the Dreamcolor is very, very linear. It's very, very stable, and CalMan can directly connect to it and calibrate its internal 1D LUT and a color matrix. It doesn't have a 3D LUT, but it is very linear, like I said, and there's no weird behavior in the color space. So we can achieve 3D LUT-like results with just a color matrix and a 1D LUT. The Z27X also has its own built-in pattern generator, and you can also use it as a standalone video display or as a computer monitor, and there's a slightly different process for calibrating both of those. In our support section on our website, we have a quick start guide that explains the two different ways you'd calibrate it. One being used as a video monitor, say as with Resolve, or one as an actual computer monitor connected to the GPU of either your PC or Mac.
Boy, that's fantastic, Tyler. Those are some great questions, and thank you for all the helpful answers that you provided. We'd really enjoy having you come to our next webinar. We're going to be going to run the next one in February. We hope you can join us. Thank you so much.